Well, we've been talking about types of contact forces. Um, Remember, let me just give you an outline of all the force types that we're dealing with. This can sometimes help you sort of be clear about when you're done dealing with the forces on a body, what kind of things you have to worry about. Um, so the force types are field forces. To us, that just means gravity. And contact forces, and that's all there are: field forces, gravity, and contact forces. And then contact forces are going to be broken up into three types of contact forces. Um, there's a pushing force, a pulling force, and we've talked about both of those already, and friction force. And so the last thing that we have to talk about, we've dealt with all of these things except friction force. So now we're here talking about the last type of contact force. Um, and so friction, this numbering system maybe is a little odd, but um, now this is the third type of contact force. So this is just the numbering system I used last time. Friction is a force that's resisting sliding along a surface. And there are actually, we can break friction down into two types. Of these two, we're only going to do one. Not because the other one's harder or easier or anything, but just for the sake of time. Um, but there are two types of friction force. The first one is static friction. And that is when an object is not sliding, and I'll say not yet sliding, because it could start sliding later or whatever, but while the thing is still at rest compared to the other object, you can think of this static friction force as trying to prevent it from stopping, trying to prevent it from starting sliding, sorry. Obviously, friction doesn't have a brain or try to do anything, but you can think of it that way. That's how it always acts. Like its goal is to, if something is at rest, to keep this thing from starting to slide along the surface. An example of that would be like if you have a big heavy box on the floor, and you start to push on it, it takes a second for it to start to slide. And until that moment when the box starts to slide, it's static friction that's fighting against your push to keep it in place. The other type of friction is kinetic friction. And that is when the object is already sliding along the surface. This tries to slow down the motion. Okay, we're not going to deal with static friction mathematically. The only one we're going to deal with is kinetic friction. Like I said, that's not because of easier or harder or anything like that. It's not because of more important or less important. It's just to do one thing that has to do with friction and not spend too much time on this topic. Okay, so an example of a friction force. So let's say that you have an incline and a box on the incline. Let's say that this box has a mass of 15 kilograms. And let's say that it's sliding that direction. Well, if we isolate the box, then there's a weight force. But as far as contact forces go, the contact all happens here at the bottom of the box. And there are actually two types of contact forces that act. There is a pushing force that keeps this box from sliding into the surface. And that's the force that's perpendicular to the surface. It follows the rules of the pushing force, perpendicular to the surface. And then there's also, what's new is a friction force that is parallel to the surface and goes in the opposite direction of the velocity. So what I said above when I was describing kinetic friction, I said it's always trying to slow the object down. Slowing the object down means applying a force that's opposite of the velocity vector. And so that's what we have here. Okay, so what do we know about the rules of the forces that happen when an object is sliding along a surface? So we're dealing with kinetic friction. And kinetic friction always happens together with a pushing force. You can't ever have a case where there's friction and there's not a pushing force applied to the object. So we are going to call that pushing force N, normal. So that follows the rules of the pushing force. It's perpendicular to the surface of contact toward the chosen body. The friction force is parallel to the surface. And in the opposite direction of the velocity vector. We also, since we're calling that pushing force N, it turns out that we always know the magnitude of this friction force. So the magnitude of this friction force is this constant, that's the Greek letter mu, times the normal force. If you ever want to sound smart at parties, know the names of all the Greek letters. This one is sort of an easy one, in my opinion, because it sort of looks like something between an M and a U. It's kind of a combination of an M and a U, and it's called a mu, which is spelled MU. So there you go. For free with your tuition money, here's hints for sounding smart at a party. So what is that constant mu? So mu is a positive number that represents the two materials in contact. Okay, so some examples of mu values. I mean, in problems, these will be given to you. But if you have two blocks of smooth ice sliding relative to each other at the freezing point, those have very low friction, and so the mu value is very low. You get a mu value of 0.02. Rubber on concrete, well, it depends a little on the type of rubber. And so we would expect this mu value to be quite a bit higher than the one for ice on ice. And the mu value for rubber on concrete is, like I said, it can vary for the different types of rubber, but it's somewhere around 0.75. Okay, so in order to figure out the magnitude of the friction force, you take this mu value that represents the two materials and you multiply it by how hard these two surfaces are being pushed together. That's the normal force, and that gives you the friction force. Okay, so now we have all the rules. We're ready to draw a free body diagram. So I'm going to draw a free body diagram of this case that I've done up here. So free body diagram of this 15 kilogram box. Okay, there's the box. Like always, there's a weight force that just acts straight down. That's 15 times 9.81, so 147.15 newtons. And at the bottom, there's a pushing force from the surface that's perpendicular to the surface, so it's at an angle, not quite straight up. And we're going to call this N for normal force. And now, for the first time, we have to know the velocity in order to know the direction of this force. In this problem, it said that the velocity of the box in this case is down the ramp. And so the friction force is going to be parallel to the surface up the ramp. So there's the direction of the friction force. And the magnitude is going to be mu times N. We've dealt with the gravity. We've dealt with all the places where there's contact with the outside world around the boundary. And so we know we're done with this free body diagram. Let's say that we know this mu value, so if this mu value is equal to 0.2, then what would this free body diagram look like? Everything would be the same, except you could just substitute that number in for mu. So we have the downward force of 147.15 1, 5. We have the pushing force. And then we have the friction force going this way. And this time we can substitute in that 0.2 instead of mu. There's a couple things I want you to notice about this, 2 things. The first one, like with pushing and pulling, there's sort of a Newton's third law type thing that you need to think about. If 2 objects are sliding against each other, so one is sliding along the surface of another one, then the friction force, let's say the friction forces on the respective objects have the same magnitude and opposite direction. So in the example we did up here, there aren't too many cases where we would isolate the floor, the ramp. But if we did, if we drew a free body diagram of a chunk of this ramp that included the part where this box was sliding, the friction force on that part of the ramp would be parallel to the ramp, but down the ramp with a magnitude of 0.2 times that normal force. And that normal force N, of course, is a pushing force. So it also would be equal and opposite to this N. And again, this is related to Newton's third law, which I'll talk about in sort of philosophically or whatever a little bit later on. But for now, I just want you to sort of have that phrase in your head. Okay, the second thing that I want you to notice is that friction is the only force that we've dealt with that cares at all about the object's velocity. But when you're dealing with kinetic friction, you have to know the direction that the object is moving. So this is the only force, including gravity, including the other contact forces, that depends on the direction of the velocity. So you can't do a kinetic friction problem without knowing the direction the object is moving. Okay, let me do an example. So let's say we have sort of a shallow ramp there and a steeper ramp there. And a pulley at the top. And let's say that on the left side, there's a 5 kilogram box. And on the right side, there's a 1 kilogram cart. And these are connected by a cable that goes over the pulley. And let's say that in this case, these objects are sliding this direction. So the velocity of that one is this way. That means the velocity of this one is this way. You might ask how that's possible. Gravity would pull it the other way, if anything. But the velocity doesn't depend on the forces that are being applied here. You could imagine that right before this instant, this system was being pulled to the left. And just as the cord between the, whatever's pulling it and this 5 kilogram box were released, that's the instant that we're looking at. So it would still be sliding, even though, maybe it would be stopping. But at that instant, it would be sliding to the left. So this is a totally possible thing. It's just that we don't know what was happening at the instance leading up to this. And we want to draw free body diagrams of the two objects. Okay, so I'm going to start with the 5 kilogram box. As always, there's a weight force. 5 times 9.81 is 49.05. And now go around the boundary looking for contact. There's a pulling force from this cable. I'll call that T. Then down at the ground, there's a pushing force. I'll call that N5. And now since this velocity is going down the ramp, the friction force is going parallel to the ramp, up the ramp. And so this is going to be mu, whatever that mu is for these materials, times N5. Now the cart is not going to have any friction in it. Those wheels indicate that there's no friction. But free body diagram of the 1 kilogram cart. There's the outline. There's a weight force of 1 times 9.81. There's a pushing force from the incline onto the wheels. So I'll call that N1. And then there's a pulling force from the cable. It's along the line of the cable, away from the chosen body. And since it's the same cable as the one connected to the 5, it has the same magnitude, so we'll give it the same variable label. And now we have free body diagrams for each of these two objects. If I had given a coefficient of friction for the 5 kilogram box, you could substitute it in for mu there. Okay, so that's it. All the rules for drawing free body diagrams for objects that have kinetic friction forces applied.